For 232J, we would just first want to draw in all the lone pairs. Now, the lone pairs we draw would be on the heteroatoms. The carbons here all have zero formal charge. Carbon only has a lone pair when it has a negative formal charge. So it's just the oxygen and the chlorine that would have some lone pairs. The oxygen needs 2 of them to get a total of 2, 4, 6, 8. And the chlorine needs a total of 3 lone pairs to get a total of 8 electrons around it. Remember, each bond has 2 electrons in it. So that's our structure, and that's the one that we're going to go through these 5 patterns with. The first pattern is an allylic lone pair. Now, the lone pairs on the oxygen are not allylic because they're not one atom away from an atom in a double bond. They're on an atom in a double bond. So those are not allylic. However, the lone pairs on the chlorine are allylic. If you go one atom over from those, you're at an atom in a double bond. And so we do have this first pattern. So we've got resonance. We tell the world by drawing those big curved arrows, the big brackets that tell people, watch out, the true structure is not any of the individual structures inside, it's the average of them all. And we're going to draw our first structure in here, exactly as it is. And when you have an allylic lone pair, the pattern of curved arrows is that the allylic lone pair goes toward the pi bond to form a new pi bond. And the pi bond breaks, the electrons go onto the atom in the double bond that's further away from the allylic lone pair. So you draw that special resonance arrow with the one line and the 2 heads. Anywhere where you have the tail of a curved arrow, first, let's copy this, put that in there, so this is where our new structure is going to be. Anywhere you have the tail of a curved arrow, those are electrons that are going to be moving, so you'll erase those. Anywhere where you have the head of a curved arrow, that's a place where electrons are going to be arriving, so you'll draw them in. If the head of the curved arrow is pointing at a bond, like it is here, then you'll draw in the electrons as a bond. Okay, anywhere where you have the tail of a curved arrow, those are electrons that are moving, so you erase those. Anywhere where you have the head of a curved arrow, that's a place where electrons are arriving, so you'll draw them in. If the head of a curved arrow is pointing at an atom, like it is here, then you draw those arriving electrons as a lone pair. Okay, for the formal charges, this oxygen, it's 6 minus 6 dots plus 1 line, that's 6 minus 7, so we've got a negative charge there. For the chlorine, this chlorine is in group 7A, so 7 minus 4 dots and 2 lines. So that's 7 minus 6, that chlorine has a positive 1 charge. So that's our first resonance structure. Now we want to go, for this first molecule, we want to go through all 5 patterns. We've only gone through the first one, so let's go through the rest. Does it have an allylic positive charge? No, there's no positive charge in there. How about a lone pair adjacent to a positive charge? No positive charge in there. How about a pi bond between atoms of differing electronegativity? And we do have that. The bond between the carbon and the oxygen includes a pi bond, and oxygen is really electronegative, whereas carbon is just average. So we'll have another resonance structure with this. Now, whenever you have that pattern, the curved arrow that goes with it is the pi electrons move on to the more electronegative atom. So we'll get that structure there. Anywhere where you have the tail of a curved arrow, those are electrons that are going to be moving, so you'd erase those. Anywhere where you have the head of a curved arrow, that's a place where electrons are arriving, so you'll draw them in. If the head of a curved arrow is pointing at an atom, like it is here, then you draw those electrons as a lone pair. Now in this structure, the oxygen is 6 minus 6 dots, 1 line, that's 6 minus 7. That oxygen has a negative 1 charge. And the carbon, just below it, that carbon has 4 minus 0 dots, 3 lines, so that carbon has a positive 1 charge. Okay. So, we're still analyzing this first structure. We've gone through the first three patterns. Let's do the fourth one. Do we have a pi bond? Oh no, we just did that one, right? We drew the resonance structure you get when you have a pi bond between two atoms of differing electronegativity. Last but not least, do we have conjugated pi bonds in a ring? No, we don't have a ring, so we don't have that. Okay, so now we can do the same thing with the second structure. Let's go through all 5 patterns. So first, do you have an allylic lone pair here? And we do. All of the lone pairs in this oxygen are allylic. If you go one atom over, you're at an atom in a double bond. But if you notice, if you do that curved arrow pattern, it'll bring you right back to your original molecule. So we don't have to draw. So although we do have this pattern, we don't have to draw anything for it. It's already drawn. The curved arrow, the resonance structure you'd get from that is drawn. How about an allylic positive charge? Do we have that? We don't. We do have a positive charge, but it's on an atom in a double bond. It's not one atom away from an atom in a double bond, so it's not allylic. How about a lone pair adjacent to a positive charge? We don't have that. We have lone pairs on an atom with a positive charge, but we don't have a lone pair on the atom next to an atom with a positive charge. Oops. How about a pi bond between two atoms of differing electronegativity? And that we do have yet again. We have a pi bond here between the carbon and the chlorine. And chlorine is just below fluorine. It's at the top right of the periodic table. So it's really electronegative. So when you have that, so we do have this fourth pattern. And when you have that, the curved arrow pattern that goes with it is that those electrons, the pi electrons, go onto the more electronegative atom. So what you'd get there is you'd have that special resonance error that tells you take the average of all these, and we'd have this new structure. Now anywhere where you have the tail of a curved arrow, that's a place where electrons are going to be moving away from, so you erase those. Anywhere where you have the head of a curved arrow is a place where electrons are arriving, so you'll draw those in. So we'd have those there. If the head of the curved arrow is pointing at an atom, then you draw them as the electrons as a lone pair. Now if you calculate the formal charges here, the chlorine is in group 7A minus 6 dots in one line, so that's 7 minus 7, it has a 0 charge now. And the carbon here is in group 4A, 4 minus 0 dots, 3 lines, that's positive 1. So that carbon has a plus 1 charge. Okay, so we're still analyzing this structure. We went through the first 4 patterns. We do not have a conjugated pi bond in a ring there, just because we don't have a ring, so we definitely couldn't have that. Okay, so we've done those, we've looked at all the resonance structures for those 2 top patterns. Let's do the bottom one, starting with the one on the left. Is there an allylic lone pair there? There's not, because we don't have a double bond. So nothing can be one atom away from a double bond. For the same reason, we don't have an allylic positive charge. This structure just doesn't have a double bond. Do we have a lone pair adjacent to a positive charge? That we do have. Now, if you were to draw the curved arrow pattern for it, either these lone pairs can come down toward the positive charge, in which case we would just get the structure above, or these lone pairs can come next to the positive charge, in which case we would have the structure above. So that, although we do have that pattern, we don't have to draw any new structures because the structures we get from that pattern we've already drawn. How about a pi bond between atoms of differing electronegativity? That we don't have because this structure does not have a pi bond. And there's no ring, so we couldn't have alternating single and double bonds all the way around a ring. Okay, so we've gone through the 5 resonance patterns for the first 3 structures. Let's just finish it off with this last one. Do we have an allylic lone pair there? There's no double bond, so it couldn't have an allylic lone pair. How about an allylic positive? Same thing. No double bond, so nothing could be one atom away from a double bond. In other words, nothing could be allylic. How about a lone pair adjacent to a positive charge? Yeah, we have that in two places. But either place will give us a molecule we already have. For example, if this, and actually this fourth structure is the same as the third structure. Yeah, those are the same things, same exact molecule. So we've already gone through all the patterns for this structure because it's the same exact thing as the structure we just did. So we can erase this. You don't draw duplicates. That'll teach me. And so we've got these structures here. Those three structures would be the resonance structures for this molecule. And so the true structure would never look like any of them. The true structure would only always look something like this. A slight negative charge on the oxygen and slight positive charges on the carbon and the chlorine. I'll just fill in the lone pairs there. And so that would be what the true structure, something like what the true structure would always look like. Notice how the charge is spread out over the molecule. It's not stuck on individual atoms. That helps to stabilize the molecule. Notice also how a lot of these bonds are in between single and double. That means that they have a little bit of a pi bond, so they can't really rotate. So there are fewer bonds that can rotate, so the molecule is more rigid. And also notice how when we draw the resonance structures, we get to see places where there are charge that you would not immediately see in the original molecule. So that would be J, using multiple resonance structures to draw, resonance patterns to draw the resonance structures for